Welcome to the presentation of our work towards Neuromorphic Control, a spiking neural network-based PID controller for an unmanned aerial vehicle. Artificial neural networks are increasingly being used in robotics and are especially useful when dealing with complex, non-linear plans. Using ANNs in closed-loop control has certain drawbacks. Prior to operation, the cumbersome process of training a network is needed. Overfitting may lead to negative performance in the case of noise and disturbances during operation. The controller latency and power usage also pose a further restriction on the neural networks where fast and efficient control is required. Therefore, simple and smaller networks are needed if they are to be utilized in a closed-loop fashion. Neuromorphic engineering is an emerging field which attempts to develop primitive algorithms using spiking neural networks. Here, we would like to present the possibilities which this new approach may present in alleviating certain challenges. Spiking neural networks behave more closely to our brains than traditional neural networks. By incorporating temporal behavior, neurons do not fire at every iteration, but only if the membrane potential overcomes a certain threshold. Neurons are connected to each other with synapses, and when a neuron fires, it generates a signal which propagates along a synapse. A specialized hardware called neuromorphic hardware has been proposed in which such networks are realized in silicon. Here, the dynamics of spiking neurons are simulated in real time and thus offer an ideal computing substrate to deploy such networks. Also, a property of most neuromorphic hardware is on-chip plasticity that enables continuous learning of the network in real time during operation. Attempts have already been made towards using on-chip SNNs for motor control, where a network was trained to generate a corrective signal if the controller starts to fail. In our work, the controller itself is realized as a spiking neural network. We implement our controller on Intel's neuromorphic research chip Loihi and demonstrate the controller on two robotic platforms. A differential drive vehicle, where we use a single PID controller to control the angular velocity, and a 1 degree of freedom duocopter, where we control the angular position using two nested PIDs. PID Control Paradigm is simple yet powerful and extendable to any dynamic system. In order to deploy this controller on a neuromorphic processor, we have to represent continuous time signals using SNN populations and also replace discrete time mathematical operations using neurons. Values can be represented in different ways with spiking neurons. Rate encoding encodes the signal in the firing rate of the neuron, while spike coding uses both the firing rate and neuron information to pass signals. In this work, we use placecoding, where every neuron in a population represents a numerical value. Although this results in a higher number of neurons required, this method allows for precise and robust representation of values. By discretizing signals into the neuron populations and by relating a spike to each desired value, we can convert a continuous time signal to a place-coded signal. Now that physical quantities can be represented with neurons, we can define operations between these in order to add and subtract these signals. This schematic shows the final PID SNN architecture, with 1D populations representing different signals and 2D operation arrays which perform addition and subtraction of these signals. These matrix operators substitute the discrete time arithmetic operations which are needed for implementing the PID controller. Combining spiking signals is easier to realize using rate-coded populations. Therefore, the PID signals are converted to rate code and summed together each with its respective control parameters. This summed output is then reconverted to place code such that the firing index can be extracted and directly passed on to the actuators. The green trace shows the control performance using a conventional CPU PID controller. The red trace shows the performance of a controller programmed on CPU with the same resolution as on the neuromorphic chip. Finally, in pink, an example run using the neuromorphic controller is plotted. We benchmark the controllers using the overshoot, rise time, and settling time average over 10 runs for each controller. These values, along with the plots, show that our SNN PID controller can perform in a similar fashion as conventional CPU PID controllers. We have incorporated Intel's research Loihi chip in a feedback loop with two different robots and shown that comparable performance can be achieved between a conventional CPU controller and a novel neuromorphic controller. The next step is to exploit the advantages which neuromorphic processors have over classic processors. On-chip learning allows connections between neuron populations to change during operation. By implementing the control parameters as synaptic weights, these features could be used to make the controller able to adapt to external disturbances such as an added weight or a malfunctioning actuator. Furthermore, the event-based handling of data in neuromorphic hardware makes them ideal for the processing of event-based sensors, such as event-based cameras, and as such we aim at exploring the field of event-driven robotics.